Hello everyone. Good evening, uh, and welcome to the PyData Meetup Berlin August session. Me and Kaushik Roy will be presenting our work on knowledge-infused statistical learning for social good applications. And so, predominantly, like today's talk would be more specific. So it's more of like developing a conceptual understanding of how knowledge graphs or prior knowledge can be integrated into statistical NLP in improving its performance in terms of getting explanations and actually making sense to the subject matter experts. In cases where you are dealing with people who are from nonprofits, specifically like medical centers or nonprofit organizations or like humanitarian organizations. So this talk, sorry, I forgot to I'll allow Kaushik to introduce himself. He and me he's right now in India and I'm in US. So we all three, like I think the meetup is in Germany. So we have three different time zones working in parallel. Okay. So this talk is in consequence with a past tutorial and a PyData talk that we gave at the Salamanca, and a tutorial that we did in the ACM hypertext, where we actually dealt with more complex applications of knowledge-infused learning in recommender systems, community networks, specifically focusing on hate speech and Black Lives Matters campaign, and talking about computer vision applications as well as information retrieval. So today's talk would be more of like developing at an abstract level of how this knowledge, prior knowledge, can be integrated into deep learning frameworks, and what are the different applications where it has seen to be giving good results, and you can actually see some outcomes which are very much relatable to what a domain expert or a person who is at the end is able to make sense out of it. So the learning from this talk is would be how the prior knowledge can be endowed into statistical learning. Uh, then what are the different forms of prior knowledges and how they can be infused into your deep learning framework. What are the existing methods that people have actually touched upon, built upon, on developing, on using knowledge graphs or prior knowledge. And we will be actually giving as so basically Kaushik will be giving a Bayesian perspective to knowledge infusion, which we as we call as the Bayesian knowledge prior. So from this entire talk, the major things that you can take away are the two things: is that explainability in AI is possible through a knowledge graph, and how is it possible? We will explain that. And in this process, how to handle knowledge-based inductive biases. Sorry, Pan. I know that you don't like explainability in AI as a term, but we apologize. It's like we actually made this presentation without knowing that. Uh, in this presentation, before we start up, I just want to give some brief definitions. When we say graph, we will be actually uttering word like graph, we are actually referring to knowledge graphs, which are graphical structures comprising of entities, relationships, and properties. When we say representation, we are actually referring to embeddings, which are varied dimensions, which are basically a vector or horizontal vector, which have like 300 dimensions, 200 dimensions, or 100 dimensions, all in real numbers. When we say context, it is basically we are talking about the text outside the training data, but is relevant to the training data. When we say abstraction, it is basically identifying the entity types. For example, if I say what you call we can say like Germany is part of the European Commission, so the European Commission can be the entity type of Germany. So that's entity type. We can look at the parent of a node, ancestors of a node. So these are need to be identified because you want to resolve the ambiguity in the content. The two different things actually talking about the same thing, but they are expressed in a different way. So the outline of our exposition for today would be talking about more of like statistical learning pipeline, knowledge representations, how we can use reinforcement with user in the loop, how we can fuse knowledge, the patient perspective, what are the different ways we can evaluate these methods, where are we after this development of knowledge-infused learning paradigm, and what are the resources that we have actually used, tested, and utilized in our projects. Why do we actually read and require knowledge in statistical learning? Let's start with a simple example where we talk about a very statistical learning framework, which involves data acquisition systems. You have millions of records. You pass it through a natural language processing pipeline, take Spacey or any other models, or you have language models of parsers. You can be taking off, like, let's say you can use BERT as one of the state of the art. You extract entities, relationships, events, and contextual features, all some together, and you pass it through a deep learning paradigm. And the deep learning model does the prediction for you, which is an outcome, which is basically the weighted features and performance scores. Now, in this process, this process raises some open questions, like, does the training data on which you built your model provided a good domain coverage? Does the labels that you are actually predicting have adequate semantics? How do you interpret the results so that the system can be adopted in practice? And did the model learn features relevant to the subject matter expert, which is pretty much important when you are actually dealing with the nonprofits? So we actually, let's just walk through a simple example. Let's take the method one, which is the traditional deep learning statistical learning pipeline, where you have a tweet. Let's say this tweet talks about flu, pneumonia, and COVID-19, and some other factors like killed 6 times more people. And you pass it through a natural language pipeline. It extracts you all the different entities possible in the tweet, and the underlined ones are the more, if you're using self-attention or an attention model, they will actually highlight to some of the words which are more important because they are more predominantly used in context of COVID-19 as other words compared to other words like flu and pneumonia. You generate representations and do the predictions. Now, in this process, you're not actually putting thrust on what are the specific words. Maybe flu and pneumonia is more important than kill or 6 times or more people. So rather than wasting time on all of these different entities, a different approach can be taken into account, where you actually pass this tweet. In through a knowledge graph, where you actually construct a small graph where you say that the flu, pneumonia, and COVID-19 are actually have a property known as affected population, because they are all some diseases, and they are all instances of communicable diseases. So you will replace this entire gigantic big tweet into just two concepts, which is affected population and communicable diseases. And you generate a representation along this rather than generating a representation for a tweet. And with these results, you actually try to you're able to develop a more interpretable outcomes. And right, you are actually getting a more information, which is, you can say it's implicit in your corpus, but it is not actually loud. It's not visible to the human eye. So this actually process is what we call it as an abstraction. And this process actually somehow addresses the two open questions that we actually raised in the previous slide, which is, do the labels represent adequate semantics? So now we have a labels which have some semantics in it, and these results are interpretable, because if the model is weighing affected population and communicable diseases, then you can know that why these two entities were actually more important than the other ones, because these are the terms which are you can actually traverse back through this in this graph. So in order to do this process, what we did was we actually leveraged Wikidata, which is basically a knowledge graph we can use, and you can query it with your keywords, just like you do it in a relational databases. Moving further, this actually raises some interesting questions in terms of statistical learning. And let's take an example of graph convolutional neural network. You know that this is one of the most powerful state-of-the-art neural network. And this neural network model does not models relationships, because it all depends on the adjacency metrics. So the question comes in how you can actually bring the relations into the entities, because in the previous slide, we actually talked about that the relationships are important for interpretability. So in this process, what we try to do is you already have, let's say, example of COVID-19 tweets. You pass through an entity embedding based model like GCN, the graph convolutional neural network, and you ask the question like, is similar? There's a similarity task, which is a very famous predominant task in NLP. The shelter in place causes anxiety, or shelter in place prevents anxiety. And the answer is yes, because prevents is not documented or recorded in the embedding stage. Whereas when you have a graph, you know that the triples, that there's a triple talking about shelter in place causes anxiety. You pick that triple, you do a factorization model over it, over the graph. You generate a representation of these triples, and you concatenate to the entity embeddings. So with this approach, you are actually forcefully putting additional information to your GCN model so that it can attend to causal relationships. And if then it will not able to find prevents as such as a relationship, so the difference becomes very large. As a result, is similar becomes false, and the answer turns out to be no. Now, moving further, we actually try to address now the two questions. Whereas does the training data that we are talking about has a good domain coverage? So when you say good domain coverage, means that the prior knowledge required for constructing the data is not considered while training. So you get your annotated data, let's say ImageNet, you talk about CFAR, you take our MNIST, you talk about other data sets in Kaggle. They're all annotated data sets have some prior intuition that the person who annotated that has in his mind, but it is not documented in the data set. As a result, the decision boundary that you create is approximated and not generalized. So another question that we have is, do the labels represent adequate semantics? So now, how do we actually try to make an approach to it? Is consider an example through on another Twitter tweet, which you has been labeled as informative. Now the label informative does not tell me which part of this tweet is responsible for that was considered as important by the narrator to label as informative. So what we did was we actually moved to a different perspective where we pass this tweet through a graph. We say which part of the entities or nodes of that graph are actually these terms in the tweet map to. So as a result, you can generate a new set of labels. And if these labels are informative, you can say create a rules of, say, let's say location and flood and death toll are important for a stakeholder. You can actually consider those labels to be important. And if these labels have some probabilities that have been generated because they are being able to map that so that because you are able to map the tweets to these labels, you are able to get a better understanding of why this tweet was labeled as informative. So this becomes more like a semantic and interpretable and traceable as well, because you can trace it to the graph. So another problem that arose in the context of COVID-19 context was basically the self-labeling of COVID conversations, because there is a humongous amount of conversations that are going online and on Reddit and other platforms on news articles on how the COVID-19 conversations can be labeled. So in this labeling process, the labeling is important because you want more and more information gathered from online media, which you can actually take, you can utilize for public health decision making. So in this process, we took a stab at it in a different, in a way that what we did was we actually took the Reddit conversations. We did a deep clustering, neural parsing, which is a very famous parsing mechanism. What we did was we able to generate some clusters, and each cluster is represented by some latent topics. These topics are the topics that people are actually discussing. Now, having these topics, can I label this cluster? Is it possible to label it? So in a statistical manner, one would simply generate embeddings of each and every of these topics and concatenate, do a dimensional reduction, find a similar topic that is very similar to this reduced representation, give the labels. That is also true, but that results in another computational aspect of it. So what we did was we just pass it through a graph. Let's say we pass it through a medical graph, and we found that these terms are actually mapped to an anxiety. So what we did was we actually found this, since there's a mapping between these terms, we actually and these terms are mapped to a very like a parent node, which is in this case is anxiety. We're able to label that cluster as anxiety. So you actually reduce your computational aspect by leveraging a prior knowledge. So now we have talked about the utility of prior knowledge, like what exactly it is. It's basically a graph. It's basically some information. But let's just have a concrete definition of and the various forms of prior knowledge. So prior knowledge, what we consider in throughout our presentation is that it is information external to the dataset, but used implicitly while constructing the dataset, and it needs to be machine readable. Like for example, you can talk about online articles. You all be aware of that there are millions of scientific articles on COVID-19 that have been made public, and which you can use to understand unstructured content. So there are textual forms of it. You have ebooks, EPUBs, and PubMed articles. which are scientific places, and you have description of entities you can gather from even the if you publish a research paper, right? Every research paper in ACM has a CCS. You can use CCS as a way to make an understanding of your article. So those becomes your entities. And the keywords that you provide in your research article, those are also a set of entities. Something very similar is in the medical literature, they call it as a medical subject headings or mesh. Now, in this, another set of the data is basically the images, which is Radiopedia and ImageNet. They both are in their own domain, one of the largest resources of information. Which you can, so Radiopedia is used to understand the radiology report and image in generating captions for the radiology images. And ImageNet you can use for the recent work in CVPR. We saw that it was used to basically develop scene understanding in those cases where you do not have sufficient data. So it's more like a zero-shot transfer learning paradigm. So in the graph-based, you have broad-based, which is FrameNet. FrameNet can be used to understand the events. It has recently been integrated into NLTK. Atomic is basically a knowledge graph, which is common sense reasoning, which says, like, let's say if X interjects Y, then not of X not interjects Y, not of X not interjects not of Y, and X interjects not of Y. So you can create all different forms of this logical forms using Atomic. And some very similar, likewise, you have ConceptNet for multilinguality. And not always you require a broad-based knowledge source. Even a domain-specific knowledge source can be useful. For example, medical terms, you have SNOMED CT and ICD-10. In Europe, we can use ICD-9 as well. They are all hierarchical structures. And likewise, we have drug abuse ontology and opioid drug knowledge graph, which has been used to understand the drug communications or drug-related communications on social media.
Okay, I just got a question about how do you figure out the knowledge graphs? Are they handcrafted by expert or inferred by some algorithm?
Okay, so how do we, so first of all, the knowledge graphs are actually constructed by default through an algorithm. So what essentially you do is you actually have a large resource. Let's say you have a scientific article, or you have, let's say I take any paper in ACM, and I pass this ACM paper through a knowledge graph, through a natural language processing pipeline, where we actually identify entities and relationships from those terms. So you can just create entity, and you can say entities, relationships can be anything that is describing two terms, and the entities, you can be like the terms as well, or you can have the events as well. So you can have this triples, and once you have this triples, what in the resource or as an index, then you can actually run a traversal algorithm to find the links between these entities, and you construct a knowledge graph. And that's how you actually create a knowledge graph computationally. Another way is what I was about to show in the next slide is, this is a graph which is created by human. So this is a SARS graph. Basically, I would say it's a more specific as a causality network that people have created that a person, like I think this image is taken from Helbing 2006, which is one of the most famous and paper on disaster management and network, where the person has actually created this graph by hand. And essentially what you are trying to do is you want to take this graph and you want to create your own graph computationally, just in keep in mind that whatever entities you're finding in that graph computationally are actually similar to the ones that have been mentioned in this thing. So you can leverage this as a ground truth resource to construct your own graph. Is it clear, or did I miss something?
Please, Sophie, ask another question if it's not clear. Otherwise, we'll just move on. Okay.
Is it clear?
Yes.
Okay. Okay, so this is basically an example of a knowledge which actually created by a human. And what we did was, in this, we just leveraged this graph and we constructed a subgraph of this. So the way we created the subgraph of this information was through manual involvement, where we say that we have the SARS, and we know that the people are more interested in some events, let's say travel bans, hospitalizations, quarantine, and we see how these terms are more important. So we have this graph for now. In this graph, we actually ignore the relationships. We are not talking about, we assume that these are all causal relations because it was derived from a graph, which is causality network. And what we essentially did was we used this graph as a entities that should guide a natural language processing pipeline. So if I'm using a self attention mechanism, I would actually try to emphasize on specifics that the attention mechanism should be actually focusing on these terms. So when we are looking at the natural language processing engine, we wanted it to actually focus on terms which are being used in social media adjacent or in the nearby context to the terms we mentioned in this graph. So if, say, let's say parents protest, so there are like, then the parent protest and schools close are has to be like, there needs to be in the close vicinity of this content. Or if there are two tweets, one where one is talking about parents protest, another tweet is talking about schools closed, we can still say that they are actually related to each other because parents protest is more relevant or more associated to schools closed. There are certain emerging events that might occur during any pandemic or epidemic or any crisis. So for that, we actually ignore some of the emerging events. We only consider those events which people have actually highlighted in the previous epidemic, and we want to we want to leverage that understanding to actually guide the COVID-19 scenario. So we actually identified entities or relationships as well as the events which are described in association with these, or are basically described in the context window of these terms. And what we did was, once we identify those terms, you took any general purpose embedding model and you cluster those entities. And when you cluster them, you are able to see that you are able to generate clusters which are more worse, which describe more worse condition, because there is one route in this graph which is more worse than the other one. For example, travel bans and economic and unemployment, quarantine. So basically, you're saying that what we have showed you as an example subgraph, but definitely you can have multiple. We have created multiple subgraphs of this kind, which represents different conditions as well. So you have cluster which is describing more worsened conditions, and then you have a cluster which is describing more like good conditions, where people are more talking about staying home and quarantine. So you can actually have discrete clusters, which if you look at it, you can actually make sense of it, because while you're making sense, you are actually leveraging this graph as a background information. Now, in this slide, I talked about a graph which is created by humans. Let's talk about a graph which is created by through computational purpose. So the one which is predominantly the large scale graph, which actually I used in my research specific to social good application, is a BabelNet. So the BabelNet is pretty accessible through Python API. You can actually get it a key and access it. And if you pass, what essentially does is that if you pass a tweet, let's say waterborne disease on rise in Texas as Hurricane Harvey water recedes, what it does is that it identifies the named entities and concepts in this tweet. So, and it simultaneously gives you additional informations. Now, there's two benefit of using BabelNet that I was able to find and was useful to me, was the BabelNet description and BabelNet hypernames. So if I have a tweet in Hurricane Harvey and I have a tweet in earthquake, can I find an association of between events that happen in two different geological phenomena? That is possible because BabelNet identifies these two as geological phenomena. So you can find some association between these tweets, since these two events are actually related through a parent node known as geological phenomena. Likewise, you can actually use this descriptions that are being provided to better understand your tweets, right? And also you can simultaneously create a parallel corpus of, so you pass all your tweets through BabelNet, it will give you all the descriptions, and then you can actually do some kind of a curation, which is kind of a manual involvement. But essentially you can create a parallel corpus and you can actually train your own domain specific embedding model, which is pretty interesting, specifically when you want a very targeted model only for a very targeted problem. So similarly, we actually utilized, so there's another problem statement for where we actually used knowledge graph, was to understand the COVID-19 related entities in the sparse news articles. So you have sparse news articles. Basically, like not all articles will be very enriched, because right now, as you know, that in COVID-19, most people are in the race of putting things out on the web. So not all the articles are very rich in the information. They are just part of it. And you want to extract entities from the sparse articles. So what we did was we took the sparse articles and we pass it through different mechanisms. One was self-attention mechanism, and another was dbpedia, which is a graph. And we found that these two sources are actually finding nearly the same information. So the only thing is that neural parsing was able to identify more information, which is not that much related to influenza, but more on like a journal purpose not information, whereas dbpedia was able to find information more like cdc and influenza like diseases. But interestingly, none of those resources actually identify that influenza is of what type of influenza was described in that news article. So that's why we use a SNOMED graph, where we pass this thing and we are able to identify that the influenza of one type is one of the another entities. So you are actually doing no computational part. You're just passing your content through a series of knowledge graphs, a series of resources, where you are able to tag more entities in your informations before you actually move on to use them in your search process for identifying more tweets relevant to COVID-19. So in this, for this building this, it was pretty easy, and we actually use some of the shelf public APIs like RDFlib, Snowstorm for SNOMED CT, Berkeley NeuroParser, and GDELT knowledge source, which actually a very large knowledge source for the news articles. Likewise, there was another interesting application that we found in COVID-19 where the knowledge graph was of use, was the identifying the depressive and what actually identifying the negative media exposure, because the media was making news and there is a negative media exposure related to COVID-19 which affected the health of a lot of people. And it is impractical to annotate all the millions of news articles. That was one of the challenges that we had. Another one is, how do we identify depressive, drug abuse, and informative tweets? When we say informative, means informative for the people and not for the public health expert. We want the information to be helpful for the public, and public do not want to get information which is more depressive and drug abuse related. So what we did was we just used a graph. This graph has been recorded in Neo4j. We actually took the concepts of this graph, and there's a vocabulary.txt file in BERT. You pass this graph, you pass this concept, or you augment this concept to the vocabulary.txt, and you retrofit the Google BERT model using a k nearest neighbor algorithm, where k nearest neighbor algorithm is a clustering approach, where what you're trying to say is that you already know your centroids and you want to position all the words near to these centroids. So that's why you actually create a new set of graph where centroids are nothing but the concepts in this ontology and all the words are nearby. And that's what you use to actually create a drug abuse BERT. And then you do a BERT classifier where you get information from two different communities. Interestingly, what we did was we just used Reddit communities as such. So the drug abuse communities Reddit were label 1, and any other community which is not in drug abuse related are label 0. And we just train a BERT classifier on this related resource. The weighted concepts that we got, we use that to actually identify their occurrences in the news articles to find the exposure of the media exposure on different parts, different states in the US. And we did a statistical hypothesis testing between what the ground truth ranking says and what is the ranking that we have provided. And it was statistical significant at, I think, 0.1%. Still a lot of work needs to be done in this, but it was fairly understandable of why these places have high media exposure. This concludes my part of the talk, where I explored the various statistical learning methods, what is the prior knowledge, how the prior knowledge can be integrated into a deep learning paradigm, and also we went through some series of examples of understanding applications like new negative media exposures, identifying causal topics in Twitter during the COVID-19 conversations, and we are talking about how we can actually extract useful entities even from the sparse news articles or sparse resources. I just hand over to Kaushik, who will be talking about the ways to fuse knowledge and the Bayesian perspective to knowledge infusion.
Thank you, Manat. So first thing that I would like to talk about with respect to the applications that we have discussed so far, you will notice that they're social good applications like COVID. So for the importance of evaluation in these models so that people can use them, we would like a human to be involved while both learning and evaluating the model. And the human provides reinforcement in various ways to aid the statistical learning pipeline. For example, here you can see that the patterns that the deep learning pattern recognition module learns, they can be evaluated by the human because the human is considered to be an expert in the domain that it's being used in. And the human can also provide additional knowledge that might be required to reconcile some of the examples that external publicly available knowledge couldn't do. And similarly, our knowledge system can in turn query the human if it requires a particular example space to contain a rule that it can't find in its database. Then next, I'd like to discuss how to fuse the types of knowledge that Manas has talked about into the statistical learning pipeline. So we at the AI Institute have explored two ways. The two flavors that we have tried are shallow infusion of knowledge and semi-deep infusion. Shallow infusion, like it sounds, happens at a shallow level. So that means at the input level. And so you have inputs for your data representations, and inputs for your knowledge representations. And we would like to combine them into a multiplexed representation. A simple way to do that might just be concatenation, the two vectors, place them side by side. Another way that you could do it is run a dimensionality reduction technique on the representations, and across those most important dimensions, you would then concatenate them so that your downstream NLP task can just use the important, most significant dimensions among all of them. A third way would be to have the multiplexing process itself be a learning problem. So a nonlinear combination of the two types of input that can be learned. But in all these three ways, the shallow infusion method tries to incorporate our knowledge just at the input level, and then it is passed on to the rest of the NLP pipeline. In the semi-deep method, we also use the knowledge to modify the parameters of the model. Any prediction function, it relies not only on the data, but also on the parameters of the model. And typically the way that it functions is that there are certain predictions associated with your examples, and it tries to learn the best fit parameter that mimics those predictions the best. And that's called maximum likelihood estimation. But in COVID-19, for instance, maybe we can't trust it because it's an ongoing pandemic. And so there may be 3 days in a row where the infection rate is 50%. And if we try to go with a maximum likelihood estimate, we'll falsely conclude that it's much more dangerous than it seems. So we would like to instead temper that sort of an estimate with regularization from a prior knowledge base. Like we know that Wikipedia, a Wikidata item on COVID-19 would show that it's a subclass of a coronavirus. So the infection rate associated with a coronavirus could be used as a more sensible initial estimate. And that could be moved towards the data likelihood slowly. And so that way semi-deep infusion is more useful in social good applications. And traditionally this can happen, I mean, theoretically that this can happen in any machine learning algorithm, but we have done it only for deep learning methods. Specifically, we have done it in neural attention models. So the popular one right now is the self-attention model. I'm sure you all are aware of it, or I hope. BERT is a transformer architecture that uses the self-attention model. Recently, GPT-3 is also based on the transformer architecture that uses the self-attention model. So what the idea behind an attention model is that you have a certain input, and in a prediction task, the model learns to pay attention to different parts of the input. As you can see here, the old school of thought and attention models before self-attention came out was, as it's shown here, for predicting that you need to provide stimulus to the economy at this point, the neural network learned to pay attention to the phrases lose their jobs, unable to pay rent, and meet basic expenditures from that input sentence. But when self-attention models came out, it started mimicking a more graphical structure. It started learning implicitly a more graphical structure. For example, the different tokens in the sentence learn to attend to other tokens in the sentence to varying degrees. And that creates a graph. And then you can create a representation for the different tokens, much like you would in a graph convolutional neural network, by aggregating representations from its neighbors. And then you use those constructed representations in a feed-forward layer to predict the outcome. Some others have also tried knowledge infusion. And Leslie Valiant, he's from Harvard. He came up with this method in 2006. So his method poses knowledge as different rules about the world, with each rule having its own uncertainty measure. Now, these rules are not independent. Depending on how they interact with each other, the infusion technique will have to define semantics to calculate the probability, the uncertainty measures for those joint configurations. Valiant called these pieces of knowledge teaching material. And the main argument, the main pro of this method, as they argue, is that it helps with robustness in the face of learning from noisy real world data. And real world data is very noisy, especially during an ongoing pandemic. And the theoretical contribution here is that they provide backbones to say, when is it worth it to construct external knowledge to infuse in your model? Because they argue that if it's too time consuming or computationally intractable, then we should just not do it. Yeah. Another way, a more neurosymbolic way to infuse knowledge that has been tried recently is knowledge infusion in BERT. BERT, again, I talked about already, is a transformer model, so it uses a self-attention framework. So you can think of this as a shallow infusion model. It uses the data from online web sources and knowledge and constructs a representation and concatenates the two. And that's passed through vanilla BERT. And here you can see an example of such knowledge, that if the number of cases in a city for COVID-19 is greater than 2% of the population, then COVID-19 and that city are probably going to be contextually relevant in the articles that follow. And it is augmented with an uncertainty scope. This way of knowledge infusion was carried out at Starling Lab at UT Dallas, and it's not neurosymbolic. Instead, it's more purely symbolic. So in inductive logic programming, which tries to learn rules from data, they use an algorithm called gradient boosting to learn the rules from data. And the additional advantage is that it also simultaneously learns the uncertainty values. And they have figured out a way to incorporate expert advice knowledge into this model during the learning process. And they have adapted this algorithm to a regression setting, to cost sensitivity constraint settings. For example, in medical domain, this is really important. If you'd much rather test someone as a false positive than not test them when they actually have an illness. So you'd like to provide that type of information to your learning algorithm. So, and a common theme in the ones that I've discussed so far is that while predicting something, they give you the best prediction, right? But in social good applications, and especially uncertain ones like COVID-19, you don't know what the best outcome is. And it's likely that all the outcomes that your model predicts are sort of have the same or similar uncertainty measures, and it's not very peaky, that distribution over the outcomes. And so maybe you would like the entire distribution and construct your own statistics on it to make predictions, and maybe construct other informative things like bounds on how correct is your answer. So with that, we see the need for a Bayesian approach that can output such a distribution. So I'll talk about how Bayesian learning can be used in semi-deep infusion and the concept of priors and posteriors. So here you can see in this architecture diagram that a knowledge prior looks like a set of rules, you can think of it as, or a formula, phi 1 that applies to an example X. And if that formula applies, now that formula could be a logical rule, it could be a path in a knowledge graph, it could simply be a set of features that are satisfied about an example. And when that happens, you basically encode as prior knowledge the probability of a particular parameter value. And because your prediction depends on this parameter value, this essentially defines what should be your initial set of sensible predictions. Then as you see more data, X, the update rule, the Bayesian update rule, shows us the probability of the parameters post seeing some data, and that's called the posterior probability. The formulas on the example still apply, so phi 1 of X and phi 2 of X still apply, and they actually help with providing explanations on the posterior as well as the prior. Then finally, with those parameters, you can use it in any downstream task. Here are some examples of structured priors. So behavioral patterns when dealing with COVID. Some leaders are more adventurous than others. And so you can put that in a rule by saying that if some leader of a country is risk averse, meaning they're not that adventurous, that implies that any parameter theta that results in the prediction f of an example comma theta being high risk should be of low probability, right? That's what the first rule says. A second example would be cost sensitivity biases. So in general, in say a country like Denmark, there could be a general rule saying that if a person belongs to a community C in Denmark, then any parameter that results in the function predicting that that person should wear a mask should be of high probability. But then you might look at some social media conversation and realize that some people in a community are tightly knit, right? Like family or friends. And so you could put that type of information in your model, as you can see in the rule before that. If a person is part of a community and the community is trusted, then you, instead of, you deviate from the general knowledge to making the probability of that type of parameter lower than high. And the third type is simple sanity checks. Like I already mentioned, instead of assuming your data estimate, which can show arbitrary things based on what happened, like 50% infection rate, you want to tell your model that that's probably not sensible. And it's likely to be Poisson distributed around the count of 3, which says something like 3 in 100 people are likely to get this type of virus. Here is another useful way to incorporate a structured prior. First, yeah. So how to incorporate fairness. So if we are trying to predict if 2 countries, how they would fare against COVID-19, and we'd like to see if development index is a good factor to consider. Now, a naive model might just think that developed countries would fare better than developing countries, and that's not a fair comparison. So we can include that in the model by tempering the effect of the developed factor. That is, actually, we would do that by sampling it from a sampling process like a variational autoencoder and setting it to mostly zeros all over, and that way it doesn't affect anything upstream. But just doing that for everything is not maybe can have other consequences. So we would like to impose structure to say that, yeah.
Excuse me to interrupt you. So it's maybe more than half an hour now. Could you think you could wrap it up in around 5 minutes so that we have some time for interaction afterwards?
Yeah, I can wrap it up in 5 minutes. in the next few minutes. Okay.
Perfect. Thank you very much.
Yeah, so here's an example of a structured prior that incorporates a fairness constraint. Like if we are comparing two countries, one of them is in the European Union, one of them is a SAARC country, then you'd like the development factor not to be considered so much. And that's what this rule is saying. So now we're going to talk about how to evaluate knowledge-infused models. And before we do any fancy evaluation, we'll do a bunch of preliminary checks, like the concepts that are present in your knowledge graph and training data. We just like to see if their representations in a representation space are close to each other. We'd like that to happen first. Secondly, we want there to be statistically significant improvement when knowledge infusion is involved. Third is that we expect the word clouds that Mana showed you earlier an example of to be more sensible when we use knowledge guided feature representations. And we can see that by eyeballing it. And when we use dimensionality reduction techniques across the significant dimensions, we expect the cluster quality to be much higher than if we didn't use knowledge infusion. And finally, because we have several humans in the loop for ethical concerns, and it's good sense, we'd like all of them to agree on the prediction outputs. It should agree with their mental models. They have to trust the outcomes, and of course it needs to be accurate. An example of a evaluation with an explanation would be, so where there's prior information in the form of structure like this, and you would think that theta development should be zeroed out when you're comparing EU and SAARC countries, but somehow the model learned that let's not do that. After its learning process, it figured out that theta should not be zeroed out. So this could serve as an explanation to the human in the loop to say that, okay, these are the type of examples where your advice did not really make sense, or the model doesn't think you're right. Where there is no explanation in your prior structure, then you have to rely on the attention weights of the attention model like I showed earlier. So where are we in AI methods for these type of applications? Initially, there were expert systems, and then when there was big data, they started using supervised learning signals into learning these policies, predictions. And then they realized that that's an expensive process to collect labels, and labels are often noisy. So they made up for the noise by referencing external knowledge sources. And that moved on to distant supervision of the type that Manas talked about a little bit earlier, that you have two drugs and you know the relationships between them by referring to the drug ontology, drug abuse ontology, and that can serve as labels. You don't actually need any data labels. You can self-label your data set. Finally, we are knowledge-infused learning methods, which just doesn't stick to just using knowledge to add label semantics, but does more than that by modifying parameters, giving you Bayesian posteriors, etc. This is code for all the methods that I've discussed and their papers. And I think it's all open source and on GitHub. So thank you. We'll take questions, and our other projects are at wiki.aisc.ai. Thank you.
Great. Oh. Okay. Do we have any question in the chat? The first one is the hardest one. I would have one. So where do you see this field going in the next year? So where do you think will be the next? In which direction should that go? What should be the next breakthrough?
So in this work, there's actually a third type of knowledge infusion that we have been looking into that would be my answer to where it's going. So it's called deep infusion. At every layer of the neural network, it represents different abstractions, right? Hierarchical abstractions. And we would like to identify those abstractions and provide different types of knowledge at each layer of abstraction. and have it be traceable to the type of knowledge that we are providing in terms of explainability and interpretability. We're working on those type of models. I think that's where the future is. Yeah.
Adding to that, so the first paper, if you get a chance to look at it, that's a BART, which is basically the Bayesian perspective to knowledge infusion. It's basically, it talks about how contrastive divergence and some of the functions that Kaushik talked about. If I can let me show you really quick. This formulation that you see, learning and inference, is what they have used to identify, to actually deduce analogy between the data sets. So once you are able to find analogical relationships between two domains, you are able to, and you have a labeled data set on one domain, you can actually leverage the analogy to actually label the another data set. So you do not need a lot of data sets for every other task. If the two tasks have some analogical relationships, you can leverage one data sets, a label data set in one domain to label another domain. And that's exactly what this paper talks about. The first one, which actually we used to explain the semi-deep infusion task. And analogy is one such application domain where we seek that use of knowledge is pretty nice. And in overall, if you summarize, basically the prior knowledge is used to reduce the amount of training data sets. And there is a startup which actually came up from Google, from Stanford, which uses weakly supervised methods, not exactly knowledge graphs, but a weakly supervised method in terms of other labeled data sets to label unlabeled data sets. So it's the approach that they is called Snorkel, which uses this a weakly supervised methods through a matrix. I think we didn't go into that much mathematics, but yeah. So assume this thing that you have an encoder and decoder, and what you want to do is you want to encode your label data set, and your decoder would be your label data set. You want your labels to be generated for your unlabeled data set using the labels for your labeled data sets. So that's the way that they define as an encoding and decoding approach, where, and at the end you have a matrix where you have all the let's say the rows would be your unlabeled values and your unlabeled data samples, and whatever you have in the column side would be the labels for those labeled data sets. So you get kind of a matrix, and the values would be the probabilities of how much this label aligns to that particular data sample.
Okay, thank you very much. That's good answer. Thank you. So we don't have any further questions. So thank you very much again for the talk. It was really interesting. I will